Hey guys, in this video I will be talking a little bit more about the inner product and the Hermitian conjugate and a few more things we can do with them. And the first thing is on a little bit of notation. I first have sort of the proper way to write something. And there are some things that physicists tend to write it in a notation that I would consider maybe not being very proper or being a little bit confusing. In a lot of textbooks, including Griffith's Introduction to Quantum Mechanics, acknowledges the notation that physicists, and admittedly that I will be using, are not phenomenal notations, and so we'll talk about that in a second. I kind of call them bad habits for physicists, but it is sort of the accepted way of writing some things. Okay, so proper, and then I've got sometimes used. Okay, so let's write this. We'll have our first example. I'll just alternate colors here. Okay, so the first thing is a ket vector. If I just write A in a ket vector. So this notation tells us a lot. It tells us that we're talking about a ket vector. A over here is the label for this ket vector, and I'll get to that in a second. But sometimes people just use A, they don't write the actual ket vector. And there's some problems with this, especially, depending on the notation that you're using for certain things. So like eventually, in section 7 especially, we'll be talking about ket vectors, and we'll be labeling them like this. We'll have like an up arrow, and then we'll have a down arrow. Okay? And hopefully you can see that the up arrow and the down arrow are not like objects themselves. They're just, they're labels on this ket vector. Actually, Griffiths, in his book on quantum mechanics, calls whatever is inside this ket vector like a serial number. For example, like sometimes when we're talking about energy, we'll label the state with the first energy. We'll label it like state E1. Or sometimes we'll even just label it 1 for being the state with the first energy instead of like phi sub 1. We'll just label it 1, or the second state 2. And so that can be a little bit confusing, if we're leaving out the vector. And so the reason sort of I'm showing this is what is inside the ket vector here, right over here, is really a label. It is a label describing the vector. The mathematical object itself is that ket vector. Hopefully that makes sense. But sometimes we will just write A without sort of the ket vector, even though maybe that's not entirely correct or really the best thing to do. Sometimes physicists will do that, and so I just want to let you know to make sure you get sort of used to that if you see it. The next thing is a bra vector, A, and sometimes that will just be written a dagger. And again, it loses some information about it being a vector, and again, A is sometimes really just it's a label on it. So I don't really like this notation, but I will occasionally use it depending on the situation. Okay, so the next thing is what happens if we multiply a vector by, in particular, a constant scalar. If I have C times the A vector. Sometimes this will be written like this, with CA and the C on the inside, which again doesn't really make that much sense because A is just the label. It's not an object itself. The object itself is the vector, but sometimes it is written like this. So, but if you ever see this, where C, and I'll make a note here, C is a constant scalar, where C is a constant scalar, you'll see this where we're doing some scalar multiplication, and it's just important to know that if you see this with a constant times, if I have something like C times phi or something in the vector, what that really means is this is just C times the bra vector, or the ket vector, and I'll talk about that for a bra vector in a second. The last thing is what is called an operator, and we have not talked about operators yet. And so, you don't need to know entirely what I'm talking about right now. So the important thing for right now, and this is our sort of first introduction to operators, is there is something in quantum mechanics called an operator that we will explore in a few videos. And we'll be using operators throughout the whole course. They're very, very, very important for quantum mechanics. And the operator will tend to represent it with a hat on top of it, which I'll show you in a second. But oftentimes we will have an operator, q hat, acting on some vector A. Okay, and this is the proper way to do it. It's the operator acting on the vector. And again, you don't need to know what an operator is exactly right now. Just, this is something to keep in the back of your head. Make sure you put it down in your notes so that when we get to operators, this will seem familiar to you, sort of the notation that we use around them. And we will often write this as q hat A with the q hat inside the ket vector. Again, this is not a good notation, and I don't like that this happens a lot of physicists use this, and a lot of textbooks acknowledge that this is really not the best way to write it, but it is how physicists write it. And so, teaching quantum physics, you want to do things the standard way, and this notation is standard even if it is not very rigorous and what I would consider really proper. Okay, so now looking at bra vectors here. So the first thing here is looking at, and I'll do this, I'll write these notes on the side, I'll do them in the right color. So let's do it in green with constant. So if I have, now instead of a ket vector, I have a bra vector, c times a. What does this notation mean? Well, in the notation that we're dealing with, what this is really CA, or I'll write it like this. This is CA Hermitian conjugate, which should make sense, right? You take the Hermitian conjugate. That's how you flip a ket vector into a bra vector. But if we remember our properties, this is C Hermitian conjugate A Hermitian conjugate, right? Because this using our the proper form here, C times the ket vector A. You take the Hermitian conjugate of the product of the Hermitian conjugates, and so C Hermitian conjugate is C star, because it's a constant scalar. It's a scalar, which is important. So we get C star A. Okay, so that's our first important point. CA bra vector is C star times A bra vector. So it's not C times A bra vector, it's C star, right? You're taking the Hermitian conjugate of this constant scalar as well. Okay, let's talk about operators now. And this one is going to, again, we don't know entirely what operators are right now, but just sort of bear with me here and keep this expression in mind. So now I want to look at what is it if I have q hat A as a bra vector. Well, hopefully you can imagine what this would be. This would be q hat A Hermitian conjugate, right, which is, this would be q hat A, that's Hermitian conjugate, which is q hat Hermitian conjugate A Hermitian conjugate. And again, really the order could be flipped, but for right now, how we're doing this, we're gonna just leave it like this for right now until we get to section 5. And then, so this would be q hat Hermitian conjugate, q hat dagger, I'll rewrite that, q hat dagger times the bra vector A. So I'll just write that here, q hat A. So that's what this notation means. If we have it inside the bra vector, it is not q hat acting on the A bra vector, okay? That's important. It is q hat dagger. You take the Hermitian conjugate. Okay, so the last thing for this part of the video is talking about inner products and what happens when we have sort of this notation within an inner product. So let's start with our constant scalars. So I'm going to bring this over a little bit. Let's bring it there. Okay. So if I have, see, I've got phi inner product with c psi. Okay, and this is sort of its own thing. Phi inner product with c psi, where c again is a constant scalar. Well, we can take the c out of the inner product. You can take a constant scalar out of an inner product. Order does not matter in scalar multiplication, particularly with constants. As we get into section 3, you'll see that sometimes we can have a scalar operator too. So that's why I want to specify that, at least right now, c is a constant scalar, and we can take it outside of an inner product. And what that would mean is this would just be c times the inner product of phi and psi. That's what this notation will mean. However, if we have c in this first part, c phi inner product with psi, we can't just take the c out, because again the c is inside the bra vector, so it's having its Hermitian conjugate taken, which is the same as its complex conjugate being taken, which means this is c star times phi inner product with psi. You can take a constant scalar outside of an inner product. Psi. There we go. Okay, so these are important to know. And then the question is, well, can I do this with operators? And the answer is no. Okay, and I want to just make this point about sort of the algebra of working with operators first, just so you can get this in your head. You can write this down to make sure that you know you can't do this with operators. So let's look at what happens if I have phi inner product with q hat psi. Okay? Can you take this q hat out of the inner product? The answer is no. Okay? What this is this is phi inner product with, or phi times q hat psi. Right? Using our properties. I'm going to bring this down a little bit. So, if I have phi inner product with q hat psi, that would be phi bra vector times q hat acting on the psi ket vector. You cannot change the order of multiplication here. Similarly, if we have q hat phi acting inner product with psi, what this is q hat dagger acting on the bra vector phi times the psi ket vector. In fact, you have to do this part first. You can't take it out of the inner product. This is not equal to q hat dagger phi psi. You can't have this operator acting on the inner product. You've got to have the operator act on phi, and then it acts on psi. And again, in chapter 5, in section 5, we'll learn more about why this is and more of the details of this. But for right now, just take me on this, that these are not the same thing. So this is what this notation means with operators. And again, we will talk about operators soon. I just want to, I felt like thematically this would be a good place to introduce this notation. So next, I want to talk about something called phases. And a phase, and I will represent this by a lowercase p, just so we don't confuse it with probability. And actually, I'll pick a slightly brighter color for that. There we go. So I'll represent this with a lowercase p. And I just want to do that to make sure we can separate it from a capital P. And this will be, a phase is defined as e to the I times some constant, or not necessarily a constant, just some e to the I times something real. And generally, we'll call that something phi. Okay, I know we use this letter for a lot of different things in quantum mechanics, but at least for right now, this is what we'll use it. It's e to the I phi. And a phase has a few special properties. And the main one that we're going to be looking at is what the norm squared of a phase is. The norm squared of a phase is, well, we know the norm squared of a complex exponential. It is 1. Okay? And now this is going to be important. This is what is important about phases. And the really important thing is, and this is, again, something you want to write down. You can multiply a state vector or state function or wave function, whatever vector, sorry. You can multiply a state vector, right, psi, by a phase, and it will have the same physical meaning. Okay, and so what that means is if we have, for example, we can have psi here, or we can have negative psi, or we can have I times psi, or in general, right, because negative 1, this is just negative 1 times psi, negative 1 is e to the I pi, I is e to the I pi over 2, so so those are definitely phases, and you know that because they have the norm of 1. And if its norm squared is 1, its norm is 1. Its magnitude, absolute value. And in general, e to the I phi times psi. Okay, these functions, or these vectors, these states, all have the same physical meaning. Okay, and we can see that. We can also see that, for example, normalization. If you multiply by a phase, you don't do anything to normalization, because if we take the norm squared, right, if we take negative, for example, negative psi norm squared is, well, that's negative 1 norm squared times psi norm squared. That's just psi norm squared. Right? Same thing here. I psi norm squared, that's I norm squared, which is 1. Right? And in general, e to the I phi psi norm squared, take the norm squared of this, that is, well, it's e to the I phi norm squared, which is 1, times psi norm squared. Okay? So, if you multiply something by a phase, it does not change its norm squared. Same thing you can show that if you have, for example, I'll write this up here, psi equals C1, phi1, I know we're using phi for a bunch of different things now, but hopefully it will make sense. If it's in the exponential, it's part of the phase, right? Plus C2, phi2, right? Again, these constants are not what we care about. What we care about is the probability, okay? And so if we have, let's say, e to the I phi times psi, then, or actually, let's just write it some phase. There we go, that's better. Some phase times psi, well, that's the phase times C1 phi1 plus the phase times C2 phi2, right? And still here, if we want, say, the probability, capital P, of the observable Q being Q1, right? So I think we've just been calling that the probability of Q1, right? This is, well, it's our new coefficient, which is the phase times C1 norm squared, right? But that's the phase norm squared, which is 1 times C1 norm squared, so that's C1 norm squared. So you keep the same probabilities. Same thing, you can show probability of Q2 would be the phase times C2 norm squared, which is just C2 norm squared. Okay, so probabilities, right? Normalization, probabilities of the observable, none of that is changed when you multiply the wave function by a phase. So it has the same physical meaning if you multiply it by a phase. Now, this doesn't mean you can multiply each term by by its own phase. In fact, if you multiply each term by its own phase, while normalization will not change. Normalization will not change if you multiply each term by its own phase. These probabilities won't change. The probabilities of other observables might. So, for example, think about the hard unit vectors and the soft unit vectors in terms of the black and white unit vectors. The hard unit vector and the soft unit vector have the same, right? The normalization is all right, and they have a phase difference, right? One of them, I believe, is like minus the hard unit vector, and the others, or minus the black unit vector, and the other is plus, or with the white unit vector, it's one of those. If you go back and look at that formula, even though the probabilities are the same of white and black, right? The difference between, say, 1 over root 2 black plus white and 1 over root 2 black minus white. I'm forgetting which one is which based on the diagram we drew, but even though these, right, you have, what this is it's just this, the white unit vector in this case is multiplied by a phase. Even though even though both of these state vectors have the same normalization, they're both normalized, you just multiplied one by a phase, and they have the same probabilities of being black and white, one of them, I believe, has this one has a 100% probability of being soft and 0% probability of being hard, and this one has a 100% probability of being hard and 0% probability of being soft. I believe this is the soft unit vector, this is the hard unit vector, right? So multiplying by a relative phase, multiplying one of them by a phase, can change the physical meaning. But for example, if you just did negative this and negative that, just multiplied everything by -1, you could show on our diagram that the probability of, for example, this one would still have the same probability of being soft of 100% and 0 probability of being hard. So overall phases do not change the physical meaning, but relative phases may. So that's going to be a really important point.